Look at any major ocean corridor today, and you'll find thousands of vessels moving cargo, catching fish, and crossing borders. We tend to assume that with thousands of satellites orbiting above us, modern technology sees absolutely everything happening on the water. But an optical satellite is effectively just a standard camera in space. It takes beautiful pictures, right up until the sun goes down, or cloud cover rolls in, or heavy smoke fills the air. For half of every day and across massive stretches of bad weather, those cameras are entirely useless. Smugglers and illegal fishing operations don't pause their schedules to wait for clear skies. When weather and darkness blind our best cameras, our ability to know what is happening on the ocean disappears, exactly when we need it most. To bypass the weather problem, aerospace engineers use synthetic aperture radar, or SAR. Instead of passively waiting for sunlight, a SAR satellite illuminates the Earth with its own microwave signals and reads the energy that bounces back. Because microwaves pass right through dense cloud cover and the satellite provides its own illumination, radar delivers highly reliable awareness in total darkness and severe storms. The trade-off is steep. A radar return doesn't produce a recognizable photograph. It generates a dense, highly technical map of how things scatter those microwaves. To a human eye, it looks like a mess of abstract static. Illicit fleets and bad actors deliberately exploit this unreadable noise, knowing they can remain visually obscured in the sheer volume of chaotic data. Collecting all-weather satellite data solves nothing if the people tracking these oceans cannot immediately translate that raw static into actionable awareness. This gap in interpretability is where a software platform called Vigilstar steps in. It acts as an intelligence layer to translate the radar noise into human comprehension. The first step in its pipeline runs the radar scatter through an AI neural network. The software scans the chaotic image to pick out bright, anomalous returns, specifically the sharp reflections created by large metallic objects. At this stage, the AI is simply answering a basic physical question. It confirms that a dense metal object, which behaves exactly like a ship, exists at a specific latitude and longitude. Using algorithms to detect and classify objects in radar is a well-established standard practice in remote sensing. It is a necessary feature, but it is not a true technological moat. Simply drawing a bounding box around a radar blip tells an operator that something is out there. Without further context, raw detection still leaves you staring at a vast, anonymous ocean. The platform's actual leverage comes from what happens next: data fusion. This is the process of correlating the raw radar hits with public mandatory tracking signals like AIS, the automatic identification system used by maritime vessels. The majority of legitimate commercial traffic complies with international maritime law, actively broadcasting their identity, speed, and filed route for everyone to see. For every metal object the radar detects, the system asks one central question: is there a known public transponder signal for this exact location? Most of the time, the answer is yes. The radar sees a massive object, the public AIS tracker confirms it is a named cargo vessel on its expected path, and the system deems that specific data point completely uninteresting. Then it deletes it. The software executes this logic continuously, rapidly burning down the haystack of data. It systematically subtracts everything that makes logical sense, erasing known variables in waves. The platform exposes the dark object, a massive metal ship physically present and reflecting microwaves, but operating in total digital silence. In a thoroughly monitored environment, the most vital intelligence is not found by amplifying the loudest signal. It is found by isolating the absolute absence of one. While this platform is packaged and sold primarily within the defense and intelligence sector, the reality of its best application is highly civilian. Finding ships that intentionally go dark is the exact mechanism needed to catch illegal, unreported fishing fleets. These operators deliberately disable their transponders to poach marine life and drain local economies unnoticed. The same fusion logic also serves a critical humanitarian purpose. When a vessel begins sinking in a severe storm and its electrical systems catastrophically fail, it becomes a dark object that Coast Guard urgently need to locate. Because fisheries regulators and search and rescue teams share the exact same need to find silent ships in bad weather, the platform's core fusion mechanic serves a broad, legitimate purpose outside of military domains. Tracking down a massive vessel that has switched off its radios serves the basic requirements of maritime safety and international rule of law. As a commercial product, the platform does require an objective reality check. The demonstrably proven core of this software relies entirely on the Sentinel-1 constellation, data provided freely to the public by the European Space Agency. The company positions itself for higher-end capabilities, claiming multi-constellation fusion and fully air-gapped military deployments. But inside the brutally slow cycles of defense procurement, those are largely unproven ambitions waiting for contracted validation. Because anyone can download the baseline radar data for free, the true value of the product isn't the satellite feed itself. The value rests strictly on how fast and how reliably their software engine can subtract the noise. When we look at this planet today, we are drowning in an overwhelming, continuous stream of raw surveillance data. The challenge is no longer capturing the image. The future of global intelligence belongs to those who can look at an ocean of noise and systematically subtract the known world until only the undeniable truth remains.